So babes, another day, another cheeky little video for you. Now what we got here is a bit of equipment that we use to temper and look after our product. Now we've got two sides of this. We've got a heated side, we've also got a chilled side to process what we work with. So what we got here is our heating chamber. We use the 3-phase heaters. We've also got a chilled side. We use refrigerant for that. Because what we're doing is we're heating up the product and then we're chilling it using friction. So, what this video is all about is a little device that I thought was snazzy and useful, but simple at the same time. And that's your thermostat. Now we've had to retrofit this one, and I'll go into that into a bit later on. But what you normally get is you get the 3-phase ones that are connected to a bulb that's fit within the heater itself, which goes between the tails and the supply incoming of the heater. Now they didn't have it supplied on this machine itself. What they did have is they had a pressure relief valve, which in this instant, it did work. It stopped the machine from boiling over and blowing up, but it blew itself like his son does in his favourite gym sock. Now, as you can see, this got really hot by the discolour of this metal. So what we did is we retrofitted these overstats on. Now, these are dead simple little devices now. This has got an actual reset button on them. Some of them are auto reset. I will go into a bit more depth on how to test them at the end of this video, but just going to go into how we've got this running through this machine and how it's going to work with the feedback as well. So we're going to go around to the old panel side of it now. Now I'm going to show you how the electrical side of it was working before. Real basic, literally just an MCB and a solid state relay. So the only way this was going to stop before is if the pump cut out. Obviously you can have stagnant water not being pumped around, that was going to boil over. That's the only way it would have gone before. And here we go. So we've got our MCB feeding our solid state relay, and then that's going out to our 3-phase heater. And there was no kind of protection apart from if it boiled, it was going to blow the pressure relief valve. So this is what we've got fitted now. So we've got pretty much the same setup, but now what we've got is we've got a 3-pole contactor in between the MCB and the solid state relay, and that's now being controlled by the signals that's coming from this common 24 rail out to that overstat through, and then that 24 is going to be the A1 of our contactor. So as long as that overstat is healthy, that contactor is going to be pulled in, which is going to be giving feed to this overstat. Because so before, it would have just boiled. So even if that welded itself shut, that solid state relay, it would have just kept on boiling. But now, when that overstat goes out, even if it welds itself shut, anything goes over temperature, that's going to kill the power. So that's our overstat coming. So it's going through our contact, pulling it through, and then going down to 0 volts. Quite simple, but really works well. And then obviously, because we want to know what's going on, if it does happen, we've got feedback. So again, that's coming from our common 24 volts. Then it's going through the overload of the pump. Now I said this earlier, if that goes out, it goes out on a heater fault because it doesn't want to boil. So that's going to go for our normally open auxiliary on our overload for the pump, and then it's going for our normally open auxiliary on the contactor that's feeding our solid state relay. Now if that's all pulled in and that's all healthy, that's going to be giving us a signal coming back on this PLC, which you can see is on. So if we look on our 9K1, and then we're looking for our input 1, and as you can see, these are all pulled in, so that's healthy, and that's showing us we're in a good state to be. Now if I speed up this process and I heat up around this solid state relay, making it think that it's popped, and there's this water jacket's gone over temp, you'll see that this now overstat will pop out, mechanically killing this signal coming back. And as you can see, the contactor's popped out because it's got no 24, because there's nothing coming through that thermal, but still sending signal to this solid state relay. But as it's got no power going through it, it can't. So the pump's in, but the contact's out because as our thermal cutout has popped out. Now, as you can see, I've now lost input 1 on my PLC. And if I go to my HMI, that's now showing I've got a failure water pump heater circuit. Now we get down to the nitty-gritty bit, how they actually do what they do and how to test them. So I've got the two main types that you're going to see in the domestic and commercial kind of site. Is we've got our thermal cutout here, which inside here we've got two dissimilar metals, normally like brass and steel. That kind of the thermal contract at different temperatures. And then we've got our bulb here that you'll definitely see in domestic and in commercial. Now this works on gases. Now inside there's going to be a bulb which expands and contracts with the changing temperature of whatever you're heating up. So obviously when it gets hotter, it's going to expand, and then it pushes all them gases up that very thin tube you've got to be dead careful with. And then what that does is changing temperature, pushes the gases back, then that pushes a mechanical switch inside of that device there. So the bulb heats up, gases expand, pushing back to our mechanical switch that then kills the feed to the supply of this heater. And this actually does have a mechanical reset on the back of this heater itself. So once that's tripped out, there will be no continuity between supply and feed of this heater. And then you can see there, that's your manual reset button on the back. Right, so let's get over to the little star of this video. Now, you got to think, the way I'm going to show you how to test this is, we're going to just do continuity across these. This is a mechanical switch. When it's hit that temperature and that bimetallic strip is bent out of the way, killing the contacts inside and breaking that bridge across, all you need to do is check continuity. If you've got continuity across it, it's good. If you haven't, you know it's duff, especially if you know the temperature is below the set point. Now, set points on these normally printed on the metal face. So as you can see, I'm now going to heat this up. This goes to about 80 degrees. And then as you can see, I've got about 0 ohms, so that's good. It's no resistance across the terminals. Once I hit the set point, now it's going to open circuit now. So you got to think, that's coming out. So on my machine, that's coming out of my block 24, and then that's going through that. But once that's hit that temperature, that's gone open circuit. Must killed the power to my contactor. And as you can see from this little diagram on the right, this is what's happening inside. So you got your bridge across there, your two similar metals that firmly contract at different temperatures. So obviously when they get to that right set point, that's going to bend out of the way. That's going to kill my signal across the bridge. Some do also have diaphragms at the back, which kind of pop back and forwards, pushing down on a pin, making that bridge. And I'll get the little diagram up here to show you them as well. But as you can see, this is an auto reset. So as that temperature comes down, it auto pulls the signal back in. But we've got a manual reset on ours, just so we're keeping it safe. Now, if you've been watching this, as always, peeps, you're ledged approved.